okay? But we'll go through this while I show you the instruments one by one, okay? So we'll start with the piston cylinder press. This is a picture here. For the scale, if I stand here, I would get up to here. So I guess that's about 2 meters, the whole thing. This is the main part of the press. This is the control board, and the compression system is down here. It's a 150-ton press, and it's a double ram, meaning that you have 2 independent rams, one that you see here, and another one that you don't see that's down here. But you'll understand what I mean when we look at the details here. So let's focus on this part here, which is blown up here. You have this big anvil. It's not an anvil. What do you call this thing? It's a vessel. So it's a big tungsten carbide and steel vessel that sits here, and you have a tungsten carbide ram that goes in a little. So this is all axisymmetric, okay? Everything is cylindrical. That goes in this, and that's being pushed by one ram, and you have another ram that pushes on the whole system. All right? So you have 2 independent rams. The 150 tons are on this main ram. You never put 150 tons here. You would just blow everything up. And your sample is this little red thing sitting here. Okay? So first you compress everything to put it at high charge so that it doesn't blow up, and then you send that ram up with, with a pressure of usually 10,000 psi, 15,000 psi. All right? So let's focus on this now. Your sample assembly, everything you're interested in sits here, and it's here, and we're going to see a detail of this on the next slide. The big lever, it's that's how you pump it. It's all mechanical. You'll see it. It's and this basically is purge and pump, and the lever, you just go like that. It's good exercise. You'll see. Oh, it's very old school, and they tried making ones where you have a mechanical pump. Nobody bought them. Nobody wants those. I mean, this is a recipe for a catastrophe. Why do you want to even use something electrical when you can just do it by hand in 5 minutes? And it's much, and you control it much better. So your sample actually sits here. Actually, let me show you on this slide. And that's basically the sample you're interested in. That's a capsule that sits around the sample. This is basically a thick MgO buffer that's holding the sample together. And what's important is this black part here. That's a graphite sleeve. And the reason why that's important is that this is the only electrically conductive piece of this whole assembly. So once you put this here, and you see those cables here, electrical here and here, you send about 600 amps through that thing. And this heats up to 2,000 degrees. And it's because electricity is only conducted by this. Everything else is insulating. So all the electricity has to go through this little thing and back out, and it has to go through the walls of this heater.
Just to be clear, the picture on the left here is actually when there's no sample, it's open.
Oh, here, oh yeah, here, yeah. If I showed you with a sample, you wouldn't see anything. So there's no sample. When you have the sample, the only thing you would see on top is this thing, right? I mean, this is this. And that is this, right? And you have this, and this is basically a pressure plate on top so that the sample doesn't ooze out. So you would have a big disc sitting here, that's it. And the gap would be closed. Okay? So the pressure in such a system is obtained directly from the load on the piston. It's basically force divided by the area. We typically use 2 different areas for this assembly here, for this piston, right? So you have 2 different pressure vessels, a 1/2 inch and 3/4 inch. 3/4 inch gives you a bigger sample, 1/2 inch a smaller sample, 3/4 inch lower pressures, 1/2 inch higher pressures, okay? So you can get up to 2 GPa with a 3/4 inch assembly and up to 4 GPa with a 1/2 inch assembly. All right. So in principle, the pressure on your sample is equal to the pressure on the ram divided by the surface, but there is some friction. So you need to calibrate that loss from friction, which you do once, and then you're good to go. You calibrate this, and then you're good to go. Okay. So this is two types of assemblies that you use, low temperature assemblies and high temperature assemblies. Essentially, if you look at it, it's identical. You have your sample inside its chamber here and here. It's a little smaller here, but that's because you have this extra layer here. Okay? This is a graphite furnace, so it heats up by sending current through and out. And if you want higher temperatures, you do it by putting another layer of insulation, which is this lanthanum chromite disc here. So basically, this is the same as this with lanthanum chromite inserted here. Okay? And just this insulation, you can gain about 1,000 degrees. So it's not so much how much voltage and current you sent through the thing, it's how much dissipation you have. And that's what you want to limit. Okay, so here you have a typical example with a lanthanum chromite heater. Insulator, sorry. You'll understand in the next slide why I said heater, because lanthanum chromite is also used as a heater for the multi-anvil. And basically at 30% of operating current, you're already at 2400 C. Okay? And temperature is measured, so this is a hole in which you send a thermocouple, and temperature is measured basically here. Okay? So this is why we have the lever. Little users. That's my son playing with the machine. And even he can do this. So this gives you an idea of the size, right? And of course, instead of looking at the gauge, he's more worried about the little guy up there. But yeah. So this is for the piston cylinder, okay? You calibrate the pressure. And no. Well, you measure the pressure on the ram.
Right.
But you don't measure the pressure in situ in each run. You don't do it with the piston cylinder, and you don't do it with the multi-anvil. The only tool with which you do this is the diamond cell.
And so you trust the fact that your machine is not aging. It's not, the friction, for example, could change with time.
No. Oh, sorry. Yeah. No. Thanks for asking. It's not the friction. It's not the friction in here, because you're measuring the pressure on the ram. So you're measuring the pressure right here. Okay? The only place where you have friction is actually here. It's this thing called halite, which is a very smart and sophisticated word to say salt. So the salt, you put salt around your thing, and that acts as a lubricant. And salt is very, and actually you have to calibrate it depending on what you're using. So we have one calibration for salt, we have a calibration for talc. You use sort of different things depending on what you want to achieve. Talc is slightly better insulating, and salt is a little more fluent. So, it fluxes more, so it gets you to higher pressure.
So I guess it depends on the size. So
Yeah.
exactly the same size.
Yeah, so that's why everything is done with a jig that has a given size, and all these things you pop out and they're identical from run to run. Yeah, you change the size of this, you recalibrate. You change the granularity of the salt, you recalibrate. How do you? Yeah, so you calibrate it once. So usually what there are materials that have electrical resistivity jumps that are known with pressure, at very moderate pressure. So you would load this in here and just put 2 leads and just compress it until you see the resistivity jump, and then you know this is your reference pressure. So you would calibrate it that way. Actually, nowadays, for piston cylinder assemblies, presses, when you buy them with your design, they would calibrate them for you. You don't even have to do this. So, yeah. That's not the case for the multi-anvil. So, yeah, multi-anvil. So, now we move on to this guy. So, for the lithosphere, I have colleagues working on the core of the moon. That's a perfect tool. You want higher pressures, you have to move to a more sophisticated workhorse. So why is this machine called a multi-anvil? In principle, it's the exact same thing. You have, and actually in principle it is simpler because you have a single ram, whereas the other one had a double ram. This one has a single ram. It's the 850-ton press, but that's not really impressive. I mean, you go to automobile garage, they have plenty of those sitting around, right? And actually that's where you buy the units pressing. I think those are more from not automobile, but boat construction. So it's a very simple uniaxial press, and what you're doing is you're going to use this very smartly designed box here called a Walker hat box that is going to transform the uniaxial press into a multi-axial press, and that's why this is called a multi-anvil, because you don't have a single axis, you have multiple axes. And the way you're going to do this, we will look at it, is that inside of this you're going to have these little tungsten carbide cubes that are truncated here with a equilateral triangle, right? And so you have four at the bottom and 4 at the top, and 4 equilateral triangles make an octahedron, which is the sample assembly here. But we'll see it on the next slide. Okay, so this is the octahedron, which contains your sample. So it's made of magnesia, and inside of this you recognize something that in principle is essentially similar to what we had in the multi-anvil in the piston cylinder press. Okay, so you have the furnace, an insulator, the sample, a capsule around the sample, a thermocouple. It's basically the same thing. Notice the sizes now. I don't think I highlighted the sizes for the other press, but it was, so you've got 8 millimeters, 31 millimeters, and now you're down to 5, okay? So it's much smaller, but smaller takes you to higher pressures, okay? 5, this is the scale, all right? But the principle is the same. And this sits inside an octahedron, which you're going to see here. So that's your octahedron, and this is the sample assembly, which is that cylinder, and it's sharing one side of the octahedron and the other one. So it's not in the axis, it's sitting like this to maximize the length within the octahedron. So it's centered on this face and goes out the opposite face. And here you have the little bits and pieces that this is made of. And this little wire is the thermocouple, okay? And these are the cubes, tungsten carbide, very hard material, that have the triangles. And so you have these little truncations here, and each truncation comes and sits and is going to push on one of those faces. So you have 4 in the bottom, and you're going to have 4 on top. You can see the truncation here, okay? So how do you transform the uniaxial pressure to a multi-axial pressure? You use this funky device called a Walker hat box. It contains 6 primary anvils and your assembly here with the 8 secondary anvils. The primary anvils look like that. So they're flat on the bottom, they would be flat on the top, and they have they're cut this way. So that's 1, that's 2, that's 3. And as you push this up, it can move together. It can slide around itself. And you're going to come and put this assembly inside of that, okay? So it falls here, and you put the top primary anvils on top. So you have 6 primary anvils and 8 secondary anvils and your sample assembly in the middle. All right, so that's the end result. The only thing that's missing here is the 6th primary anvil. Actually, I think there's also a cube missing. And above all, this won't work because it's open. But that's the basic principle. So you're transforming a uniaxial load into a 6-axis load that is going to come and push on 8 little cubes. All right? And inside the octahedron, the assembly is basically identical to the piston cylinder assembly. So now pressure calibration, same thing. Here you can't assume that you have pressure divided by surface with a little bit of friction. That's not going to work because the surface is a funky surface. It's deforming, and there's a lot of friction on the primary anvils themselves that transform the uniaxial pressure into a 6-axis pressure. I mean a 3-axis pressure, right? So here you have to calibrate using known phase transitions. The one that most people use in the geological world are olivine wachsleite ringwoodite. Now what's funny is that this is the press that was used to discover olivine wachsleite ringwoodite, right? And now you use this as a calibration for the press. This is how it goes. Initially, the old ones were calibrated with quartz, coesite, stishovite. So these are transitions that occur at higher and higher pressures and temperatures. You can also use aluminum solubility and bridgemanite, metal insulator transitions, just as was in the case of the piston cylinder press. And if you have one of these presses on a synchrotron, then you can do in situ measurements with X-rays. Okay, so it's interesting because this is not exactly the way I want to look at it. I want the little. So there is a little opening for X-rays to go through these little assemblies. And you wouldn't use cubes that are exactly like that. They would have a little opening here, just something very tiny, less than a millimeter. And you can send X-rays through and collect X-rays on the other side. And that's for people who do radiography or that do X-ray diffraction to measure the density of materials. Okay? Okay, let me go back. There's one thing I forgot to say. Quiz time, quiz time. All right, quiz. Let's see if you're listening. So here, if you look, you'll see no graphite. I told you it was identical, but not quite. There is no graphite here, and the furnace is this black material here, which is lanthanum chromite. Do you have an idea why we don't use graphite in this furnace? Oh, come on, man. I'm not asking you. Yeah, because as soon as you get to the pressures where this thing is operating, graphite turns to diamond. We're all very sad, right? Well, actually, yeah, for the sake of the experiment, you're sad. So, and diamond is an insulator, and it just stops heating. It's actually pretty impressive when you see it happen once, and then you hear a big pop. Okay. So it's this tool. And just for the history of things, this was the main press that was used back in the 60s in the study of mid-ocean ridge basalt petrogenesis and people, like Ringwood, working on basically, the composition of the primitive upper mantle by looking at peridotites and basalts and estimating, what sort of mixes you need to make to get to something that's gives you a broadly chondritic composition. So the experiments were performed in this. And as I said earlier, the olivine ringwoodite wachsleite transition and the discovery of these transitions in the transition zone was made by the Japanese using this press. Okay? And now we're going to move to the laser heated diamond anvil cell. So it's a very simple design. It's a uniaxial press, but now the anvils aren't tungsten carbide, they're diamonds that you see here. This is it's not exactly a zoom in on this. These are clean diamonds, these are horrible. But it gives you an idea of the principle. And basically you have two gems that have been truncated at the bottom to have a flat surface. And you put a little foil that's going to serve as a gasket. And your diamonds are going to press on the foil. You're going to recover the foil. You're going to drill a little hole. You're going to put the foil back. Then you put your sample in the hole. Then you close the diamond, and off you go. All right? This is how you make your assembly. This is how you create your sample chamber. You see it here. You got a gasket, diamond, sample, pressure marker if you want. And what's interesting with diamond is that it's transparent. It's not like tungsten carbide, right? It's transparent to a wide range of radiation. I mean, it's transparent in the visible. You can see through it. Here, you're looking at that sample through the axis of the diamond, all right? You light it from below, and you look through a microscope from the top, and that's what you see. So this is this guy. And also, it's transparent to the infrared, to X-rays. So you can use all these radiations to probe your samples in situ, which is impossible to do with the other techniques, okay? So you increase the load on the diamonds, this thins down and pressure increases, okay? So it's transparent to the infrared. You say, why the infrared? Well, remember, infrared it's the color of heat, right? So you can send an infrared laser on your sample, just like that, and your sample heats up where it absorbs the infrared laser. Okay? And this is how you can achieve temperatures higher than 4,000 degrees. So here's a picture taken in my lab where you're actually looking through this hole here. You know, zoom out, and this is just taken with my phone. And the only source of light is that little piece of sample which is being heated up on a 20 micron spot, and it's filling out the whole, I mean, partially the whole room. But you can see a lot of light coming out through it, okay? So this is how much light you put in the system. This is what the system looks like. That's the diamond cell that you recognize here. So that picture was taken from here, you know, with the light coming out this way. I'm not going to describe this at width because there's at lengths because there is a ton of optical components, but basically this is the laser. It's an infrared laser, a high power 200 watt laser that comes in, is split in two, goes this way, that way, through two lenses, focused on the sample in the same spot from the two sides at the same time, okay? So the infrared goes this way, the visible goes out. These are special mirrors that reflect infrared and let visible go through, and the visible will go through all the system to the spectrometer, and this is how you measure temperature by spectroradiometry, by looking at the color of the light that's coming out. Exactly in the same way that you measure the temperature of a star, okay? And this is a record of temperature here. So, yeah. Do I have a picture? Do I have a film? Oh, yeah. So this is my other son doing the experiment. He's older, so he's entitled to do laser heating. So here's a film that I made with my phone. I'm sorry, it's not great, but actually it's great that phones can do this nowadays. So this is a basalt that's compressed. I'm turning the lights off, the lights that allow you to see the sample, and that's the light coming from the part that's being heated by the laser, okay? So this is the sample here. All the dark are places where our laser heated before. This is the stuff surrounding the sample. This is sitting at about 55 GPa, so sort of mid-lower mantle depth. And I'm what? No, I'm looking now. I'm looking now. Yeah, I'm looking through the diamond. Actually, I'm filming a TV camera. That's why, with my phone. That's why it's moving. But otherwise, it's perfectly static. I mean, you see that my hand is moving, but the thing itself just doesn't move. And your laser is here, and it's very bright. Oh, and turning off the light and on to see the sample. And when you turn it off, the only source of light that you have is the light emitted by thermal radiation. That's about 2500 C. Okay. It's funny. We measure temperature in degrees centigrade in large volume presses and in Kelvin in diamond cells. It's like a tradition. I don't know why. Yeah, 273, right? You don't even have to multiply. Just add something. Okay, so here are... Do you have any questions? I mean, here are the three basic types of presses that you would find in most earth science research institutions. Maybe they don't have all three, but you know, if they're specializing in the lithosphere, you're bound to find many of those. If they're specializing in the upper mantle, they would have these. If they're doing more lower mantle and core work, you would find this. But these are basically the three sort of standard ubiquitous tools that you find to generate high pressures in research labs. Do you have any questions? Technical questions? A question? Something that I did not address? Yes. I can't do 2 GPa in a diamond cell. It's too low. Okay. Yeah. And my pressure gauge has an intrinsic error of 2 GPa. But I see what you, I mean, but I could ask your question at 25, and that should be doable, right? I mean, between the multi-anvil and the Oh, wait. So I'll show you. Okay, so you'll have an answer on, no, what's today? Tuesday, Wednesday, Thursday. I'll show you something. That's cool. Yeah. And the answer is yes. So these are the experimental techniques. Okay, what time is it? 15 minutes? Do we want to rush through this? No. We don't want to rush through this, right? No. Okay. So let's just take it easy. So you've got your tools. They allow you to generate pressures and temperatures that are relevant for planetary interiors. Now, what layer you want to study, what part of the interior you want to study will tell you which press you need to use. But once you've got to that point, you have to do something. I mean, it's one thing to generate the pressures and temperatures on the materials that you're interested in, and it's another thing to be able to say something about what pressure and temperature does to them, right? So two big classes of techniques, analytical techniques, okay? You have the in situ techniques and the ex situ techniques. In situ techniques means that you're carrying out the measurements of whatever property you're interested in while the sample is at high pressure and temperature. So say you compress it in a diamond cell, you put the lasers on, you're sitting at 50 GPa and 2300 Kelvin, and you're very happy, and these are the conditions you want, and you want to measure the elastic modulus of your sample. Boom, you can do it at the synchrotron if you're on the right beamline, and if you're lucky, okay? And you have ex situ techniques, and these are measurements that are made on samples after they're recovered. So they're basically what we call cook and look. So you basically compress the material, you take it up to the temperature you're interested in, you quench it, you just drop temperature, release pressure, get your material out, and then you study it. And both have their pros and cons, okay? So the in situ techniques are mostly diamond cell techniques. There are some in situ techniques on piston cylinder, on multi-anvil and other types of cells called Paris Edinburgh, but I'm not going to, these are like niche sort of things, but most of the in situ work that you see nowadays in the high P and high T world comes from the diamond cell. And it's basically limited to whatever it can get in the diamond cell. Well, but, and as we said, the diamond cell is a pretty versatile tool in terms of diamonds being pretty transparent to almost anything. So visible lasers, you can do Raman and Brillouin spectroscopy. Infrared lasers, we already used them and you saw it for heating, but you can also use them as a pump probe technique. There are many things you can do with this. It's a booming field nowadays. X-rays and everything you can do with X-rays, diffraction, spectroscopy, absorption spectroscopy, emission spectroscopy, inelastic scattering, Raman scattering, non-resonant scattering. I mean, a ton of things that you can do in a diamond cell in situ. And you say, okay, if I can do these measurements in situ, why do I even want to bother and do anything else ex situ? I mean, isn't in situ better? It is better, but there are things that you cannot do in situ. And this is why you use a lot of ex situ techniques as well. The reason is everything goes. I mean, once you recover your sample, it's sitting outside in your hand. It might be tiny, but you can probe it with anything. You don't have diamonds sitting there or tungsten carbide cubes sitting in your way, right? And this is mostly electron and ionic beams. You can do mass spectrometry. You can do scanning and transmission electron microscopy. So you can go and now start probing your sample at the nanometer scale, okay? You can do microprobe analysis, where you can measure the composition of like tiny parts of your sample with very high analytical resolution. You can use ions, you know, like cesium ions, oxygen ions, or lasers to do laser ablation mass spectrometry. To measure, I don't know, isotope ratios or concentrations of trace elements with very high resolution on those high pressure phases, right? They're not at high pressure anymore, but whatever they froze from their high pressure, high temperature life is still there, right? So these are the two sort of categories. We'll start with this, and we might leave this for tomorrow, okay? So the main tool for in situ analysis is the synchrotron. You all heard of synchrotrons? Yeah? You hear of us going, oh, these guys are going to the synchrotron. Okay, this is the synchrotron. It's this big old machine, crazy environment. I hate it, but you can do a lot of things there. It's basically a huge ring with electrons going around very fast at the speed of light. And everything that goes around is always being accelerated, right? And as you know from electrodynamics, a charged particle that's accelerated emits radiation. And at the speed where they're accelerated and with the radius, I mean with the acceleration that they have, they are emitting in the X-ray part of the electromagnetic spectrum. So basically, at each one of these, what they call insertion devices, it shoots out not electrons, it shoots out X-rays, basically like a laser that comes through these little beam lines where you put your samples, your detectors, computers, people. All right. It's no people, not here. Here, okay. Your enemies here, your friends here. Okay. So basically, you got these electrons running around at the speed of light, emitting X-rays, and people are sitting here day in, day out, and measuring stuff. All right. Of course, X-rays. First thing you do with X-rays, the first thing you do with X-rays is X-ray diffraction. You all know X-ray diffraction. We're not going to do a crystallography course here. I'm just going to show you Bragg's law, and it basically tells you that you have a periodic network of atoms in whatever you're compressing in your diamond cell, and you send X-rays on it, and the only constructive interferences you're going to have are for certain distances, which correspond, macroscopic distances, millimeters on a detector, that correspond to nanometers in your sample, which are the interatomic spacings, okay? Following this law, all right? So this is the interatomic spacing. This is the wavelength of your X-ray. N is always equal to 1, and theta is the angle that you're looking at, okay? And what a spectrum looks like, and that's what a spectrum looks like. So that's your angle here, 2 theta. So yeah, it's theta in the equation, and they always plot it as 2 theta. Just don't ask why. And basically, you have a peak that is where each peak corresponds to a certain d-spacing in your sample, okay? So this is a periodic d-spacing, so it's measurable. Then there's this one, right? Then there's this one. Then there's the third diagonal, and it's in 3D. So you can imagine all the combinations of, it has to be periodic to give interferences, constructive interferences. But you can measure all of those distances, and once you get all of those distances, you can work out the size of the lattice of your crystals. And if you know the composition, you know the size, you know the volume, then you know the density, all right? And this is how you measure the density. This is MgSiO3, which is Bridgmanite at that temperature. Where's the pressure? So 80 GPa. No. This is a 2, not a 1. 2681K. And these are the lattice parameters. So you multiply, so you know what the lattice parameters are, right? Oh, I'm not. Can I erase your PK little IKP, Ed? Phone numbers? No, not Philippe. We want to bug Philippe. Okay, so right, you have your, let's take something simple, cubic, right? So you got your atoms sitting here, right? Okay, you got A, B, and C. Well, when A, B, and C are equal, it's cubic, otherwise it's orthorhombic. And basically, your volume is A times B times C. And that's going to give you the size of this that contains all those atoms, right? So all those atoms are shared with 8 others. So even though you have 8, you have 1 atom per cell, right? So you have the volume of the cell. You know the molar mass of the cell. If you know your atom, say this is iron, so it's 55.8 grams per mole. And that gives you the density, right? Which is M divided by V, right? And this is something directly measured by these guys. I take it back. Modeled from the measurements of these guys. Okay, so this is why you measure this. A typical example, why is it doing this? Okay, so here we're just changing pressure. It's like the same thing, 15 GPa, 22 GPa, 28 GPa, and it's not working. Pressure is here, right? This is hematite. And what you see is that all the peaks are remaining the same but shifting to higher angles. Higher angles mean smaller d-spacings. and it's normal because as you increase pressure, volume shrinks. So this is what this is showing you, okay? And he keeps doing it. I can't, it's like a day without end. Okay, here we go. So here you can have the same sample at, this is when you load it in the diamond cell, it's sitting at a few GPa, and then you start increasing the pressure, almost getting to a megabar here. And what you see is that all those lines shift to higher angles. And what you also see is the appearance of new lines, like a shoulder here. This has appeared, it wasn't here. I think one is disappearing, but I can't see which one. This one. No, it hasn't disappeared. But you have new lines appearing, and this means that your crystal structure is changing. So not only can you calculate or measure the volume of your crystal and then get the density, you can also see transformations in the crystal structure, in the atomic arrangements. Say all of a sudden those atoms say, we're too squeezed, we don't want to be this way. You are going to go to the middle, and here we're going to have like 1 out of 2, all right, like this. All right, here you go, phase transition, right? And you would see it by seeing new peaks appear and usually old peaks disappear. Okay? I'm not going to go into crystallography. I just want you to know that this, all these measurements are made in the diamond cell, and this is typical of what you can do on a synchrotron beamline. All right? So you can have density at any P&T in principle. Density being one of the main parameters that we're interested in. Okay? All right. Now, what should we leave like in 4 minutes? Okay, so let me stop here. I'll finish tomorrow. Because then now we're going to go to like hardcore stuff. Not now. Yeah. Okay. C'est agréable,